Okay, picture this. A train. Hundreds of tons of steel just blasting along at the speed of a jet. But here's the thing. It never actually touches the track. It sounds like something out of a sci-fi movie, right? Well, it's real. It's called a maglev. And we're going to break down exactly how this incredible machine flies.
So you gotta be asking yourself, how on earth does something that massive just float? It seems like it has to be magic, but the answer is actually way simpler than you think. It all comes down to a force you've been playing with since you were a kid.
Yep, it all comes down to a magnetic secret. And don't worry, this isn't some high-level physics class. It's really just one simple rule that unlocks the whole thing, making this crazy piece of engineering something we can all totally get.
You know this one. We all learned it with refrigerator magnets, right? Opposite poles, a north and a south, they pull together. But try to push two north poles together, or two south poles. They push each other apart, and with a lot of force. Both of these effects are important, but for a maglev train, one of them is the absolute star of the show.
And this is it. This is the whole secret right here. That powerful pushing force, repulsion, is basically the engine, the wings, the whole shebang. If you can just hold on to this one idea, the rest of it is a piece of cake.
All right, so let's put that rule into action. First up, step one is the lift. How do we use that simple little push to make a multi-ton train actually float?
So here's our setup. We've got the train, and we've got the special track it runs on, which is called a guideway. Now, from the outside, it just looks super sleek, but all the real magic is happening in that little gap between the two. So let's slice it open and take a look inside.
This, my friends, is magnetic levitation. That's where maglev comes from. We're talking about incredibly powerful electromagnets that lift the entire train completely off the guideway. And this is so important because it gets rid of the #1 enemy of speed, friction. When there are no wheels touching a track, there's almost no resistance holding it back. So let's break that down. You line the bottom of the train with powerful magnets, then you line the top of the guideway with magnets too. And here is the genius part. You make sure that the like poles are always facing each other. So north is facing north, south is facing south. And what do we know about like poles? They repel. It creates this powerful, invisible cushion of force that's strong enough to just push the entire train up and hold it suspended right there in midair.
Okay, so our train is floating. That is awesome, but it's not actually going anywhere. So now we need step 2, the push. It's time to turn on the invisible engine.
And this is the logical question, isn't it? If there are no wheels to turn, no engine gripping the track, what in the world is actually providing the push to move it forward?
The answer, it's brilliant. The guideway itself is the engine. I want you to think about a normal electric motor, the round kind that spins things. Now imagine you could just unroll that motor and lay it out flat, all the way down the track. That's a linear motor. It creates a magnetic wave that ripples down the guideway, and the train literally gets to surf on it.
So here's how that wave works. The magnets in the guideway are flipping their poles constantly. First, the track creates a north pole right in front of one of the train's south pole magnets. Opposites attract, so the train gets pulled forward. But the instant it passes that spot, the magnet in the track flips and becomes a south pole. Now you've got two like poles, south and south, right next to each other. And what do? They repel. So the train gets a powerful push from behind, sending it even further down the track.
This isn't a slow process. This is happening thousands of times a second. It's a perfectly timed dance of pull then push that creates this seamless, invisible wave, just launching the train forward at incredible speeds.
Okay, let's put it all together. You've got the levitation, the magnetic cushion lifting the train up. Then you add the propulsion, that magnetic wave that's constantly pushing and pulling it forward. When you combine those two things, the result is just pure frictionless speed. And how much speed are we actually talking about here? Well, the current world record for a maglev train is a staggering 603 kilometers per hour. That's more than 370 miles per hour. I mean, to put that in perspective, that's fast enough to get you from Los Angeles to San Francisco in about an hour. Just wow.
And this is exactly why floating is such a game changer. A traditional train with wheels is fighting friction every inch of the way. That creates heat, it causes wear and tear, and there's a very real physical limit to how fast you can go. But with magnets, there's no contact. That means no friction. And that means the potential for speed and efficiency is just on another level. So when you think about it, this mind-blowing technology, all of it, it comes from that one simple rule about magnets pushing each other apart. It really makes you wonder, doesn't it?
Are we looking at the future of high-speed travel right here?
So we've seen how maglev gets rid of friction to hit unbelievable speeds. But that kind of opens up a much bigger question, you know? If we can master frictionless travel in a train, what other huge problems could that idea solve? It's a pretty fascinating thought.